Okay, hello everybody. Welcome to the beginnings of chapter 6. Here's a quick overview of what we'll be doing. So we'll be looking at vectors and a little bit more of vectors. And if you have taken physics, you've probably heard of vectors already. I don't think we go quite into much detail as physics does, using them for force and that sort of idea. But we're going to do more of the math-based stuff on it rather than the physics and that sort of stuff. So you'll see what I mean as we get going. Then we're going to look at new types of graphs, new types of equations called parametrics and polar equations. You actually can do them on your calculator, so we'll look at those as we come up. And then the last one, I think my favorite section of, probably my favorite section of the quarter, is this thing down 6.6, and it has to do with the nth roots. We'll get there when we get there, obviously. All right, so let's go ahead and go forward. Let's look at vectors, the basics of vectors, what they are, what they represent, that sort of good stuff. All right, so vector in general is a directed line segment, PQ, and we indicate this just like we do in geometry. You know how we used to put segments and that sort of stuff. Vectors get this symbol across the top. At least they do for me. I think other classes, other textbook might use a slightly different variation, but this is the one that I do. It's kind of like a half arrow thing. Okay, so it's a directed line segment. It starts at P. So my initial point is P, and my terminal point is Q. So it would look like this. Here's P. It would go in this direction, in the direction of Q. All right, some text will put this up here, so let's put this up here. So it's a directed line segment. It's going from P to Q in that direction and that direction only. All right, so one of the things that we deal with is what we call magnitude. This is going to be a very good name for us, good word for us to remember. Magnitude, most of you probably know that magnitude represents size, and that's also defined by length. And there's a very specific symbology that we use here, and it looks like this. Let's see if I can write that a little bit clearer. So we take our PQ, we take our vector PQ, and we do this to it. Now that looks like absolute value, but here's where you have to make big notice of context. In this case, we're dealing with a vector, and therefore that means magnitude. And if you might remember, the absolute value does mean length. It means distance from 0. So in our case, vector is really just vector. We're eventually going to get to 0, 0, but it's really just length. And length, I mean, if we have 2 points on a graph, we know how to find length. Okay, so you have to understand the absolute value here. This is not absolute value. It's magnitude. Okay. Now, most often when you are in a math class or maybe even a physics class, we let vectors, we don't usually use 2 letters here. We usually just say it's the vector u or the vector v or w or whatever, but we use a lowercase bold letter. So we could say something like, hey, find this. That's my version of bold. Find the magnitude of u. Okay? In real life, and like I said, if you've been in physics, you've probably dealt with this a little bit. Force, velocity, and acceleration, or speed even, are representations of vectors, or vectors are used to represent these 3 things. Force, like Newton's, Gauss, I think, is a force. Just different forces, velocities, and accelerations, that sort of idea. We're going to look at some velocities here coming up. And one thing I'm going to come to on this next slide is 2 vectors are equal if they have the same direction and the same magnitude. So if I had PQ up here and I had RS, those kind of look close to similar. Notice that they're going in the same direction. And they have what looks like the same magnitude. So I could say these two vectors are equal. But if I went like this, and let's say that's mt, this wouldn't be equal to either of these because they're not in the same direction and same magnitude. So what we need to figure out is how can we describe direction and how can we describe magnitude. So I'm going to give you a little bit of information here. We're going to let u be the vector represented by the directed line segment from R to S. So we're looking at a vector RS going from the points -4, 2, so we'll call it here, -4, 2, to the point -1, 6. That looks like right about there. So that would be a representation of my vector. But then we're also looking at the vector going from O to P. Anybody want to guess why it's called O? Oh, I heard everybody say because that's the origin, mister. Right? So going from O, which is 0, 0, up until the vector or the point 3, 4. Now, I might have drawn them to make them look like they are equal, but we have to verify this. So one way that we can do this, we'll do it a little bit differently later, but right now, one way we can find direction is by actually finding slope. And some of you may have been finding slope already, going, oh, this goes from 0 to 3. This goes from -4 to -1. This goes from 2 to 6 and 0 to 4. Oh, they look kind of equal. We can find the slope to describe the direction. And then I mentioned something about magnitude or length. We have this handy formula called the distance formula to find the distance between 2 points. Well, distance is length. So we can find magnitude by finding distance. If you forget what that is, which everybody seems to forget, it's the distance between the y values squared plus the distance between the x values squared. And if you remember, that's Pythagorean theorem, different version. So we can figure out if these two vectors are equal by finding the slope. Well, the slope for RS, let's just start with RS here. Slope is, it rises 4 and runs 3, so slope is 4/3. My distance is, well, if that's how much it changes in y and how much it changes in x, it's 16 and 9. So it's the square root of 25, which is 5. Well, let's look at OP. OP, the slope for this is it rises 4 and runs 3, so my slope is 4/3. That's looking good for us. Oops, not 4/4, that's silly. 4/3. And the distance is, well, it rises 4 and runs 3. Well, that's the same idea as for distance here. It rises a total of 4, runs a total of 3. So my distance for this one is also 5, and therefore they are equal. So as long as you can show their slopes are the same and their distance or their length is the same, you're all good, or magnitude. All right, so let's keep moving forward here. Component form is how we are going to write almost every single vector. We're going to say the vector u is something. And we don't ever, we almost never write them as going from one point to another point. We always start with an initial point at 0, 0, which means we're going to have to move things around. And what this is saying is that all vectors that are the same length and the same direction are all the same vector. Doesn't matter where you put it. All of these vectors, that's kind of ugly, let's try again there. In component form, vectors are always written like this, where it is an x, comma, y. Starting at 0, 0, going to x, y. So this component form is written as triangle brackets here, x, comma, y. That means it starts at 0, 0, goes to the point x, y. So if I said, hey, draw the vector 2, 3. Oh, that would look like this. Starting at 0, 0, going to 2, 3. That would be that vector. Easy. So what if I was to give you one of those other vectors where I said, hey, let's start at P and go to S, but I want to write it in component form. So if I thought about this, -2, let's say 5 is right there because I got to go to 8. And -1, 8. And I'm going to go there. My initial point is at -2, 5, which means I need to move it in order to get my, and here's what I'm getting at. I'm getting my initial point down to 0, 0. So I need to move it to the right 2 and down 5. So I have to add 2 and go down 5. Well, I would have to add 2 and go down 5 as well for that new point. Well, adding 2 is going to be 1, and going down 5 is going to be 3. So that means this vector is the vector 1, comma 3. Now, a much easier way to do that rather than looking at the graph is simply by doing the vector is the change in the x-coordinates, so -1 minus -2, comma 8 minus 5. So the terminal point minus the initial point will get us the component form of the vector. Oops, +1, comma 3. That's pretty simple. All right, vector operations. We're going to let U be the vector AB and V be the vector CD. In addition, very, very simple, addition of two vectors is just the addition of their corresponding parts. So this is A plus C, and this is B plus D. Excuse me. Thank you for everyone said bless you. All right. So addition's pretty simple. Subtraction's the same thing. You subtract the corresponding parts. This vector, by the way, I'm not sure if I say it coming up. This is called the, oops, not component. This is called the resultant vector. The vector that is the result of addition or subtraction or anything like that. The resultant vector. Oh, I said it right there. Look at that. Sum is called the resultant vector. We could also multiply the vector by any number we want. K is just what we call a scalar because it scales the vector up or down. It makes it longer or shorter. And we would just say, okay, K times U would just be the vector KA, comma, KB. So we're shrinking the X values, shrinking the Y value. We're actually going to use the scalar here coming up just a second. Oh, and I didn't really mention this yet, but if you were to think about finding for component form, since component form starts at the origin 0, 0 and goes out to a point A, B, finding the magnitude of this just became a lot easier because it becomes the square root of A minus 0 squared plus B minus 0 squared, which is actually just the square root of A squared plus B squared. Well, that's nice because now I can just, if I'm in component form, finding magnitude is super, super easy. So the magnitude of U is just the square root of A squared plus B squared. The magnitude of V is C squared plus D squared, or square root of C squared plus D squared. Okay, so that's going to come in handy. I'm going to go over this parallelogram law on the board over the next couple of days because I kind of want to just show it. It's not going to be super important for what we're doing, but it's kind of a cool little parallel, a little law that goes along with the vector operations. All right. Oh, did I mention there's a lot of little things in this section? If I didn't, I'm doing it now. Okay, a unit vector. You might remember the idea of a unit circle. If you recall, a unit circle meant a circle with radius 1. Well, a unit vector is the same idea. It's a vector with magnitude 1. And sometimes these come in handy for some of our harder problems. Finding a vector that goes in a certain direction but only has a magnitude of 1. And what we want to do is we want to change vectors into a unit vector. So if v is not the 0 vector, then u is the unit vector in direction of v, and I'm going to write what u is going to be here. So if I let v be the vector a, b, just two different numbers here, it doesn't matter what they are. I could find the magnitude of this vector, and well, what I want to do is I want to take the magnitude of this vector and I want to make it equal to 1. So what I want to do is divide by that vector, or by that magnitude. So what I want to do is I want to say it's 1 over the magnitude of v times the vector u. And let's say the u vector is c comma d. I know I did it backwards from what was on the other page, but 1 over the magnitude of v times the vector u. And that really is, that's now the vector, the unit vector in the direction of v. So let's look at this as an example. If I said my vector v is -3, 2, and I wanted to find the unit vector in that same direction. So first of all, I got to find the magnitude of v. Well, that's going to be nice and simple. Square root of 9 plus 4, so 3 squared plus 2 squared, is radical 13. Well, that means the unit vector is 1 over radical 13 times, oops, I'm sorry, up here this was supposed to be times AB. That was my fault. Sorry, guys. It's 1 over the magnitude of v times the vector v. Duh. So I didn't really need this. Okay, so 1 over the magnitude of v times the vector v in the first place. And that's actually it. You can leave it like this, or you can multiply it through. You could simplify these fractions as well. But what I want to verify here is the magnitude is actually equal to 1. So I'm going to find the magnitude of this new vector. I know it's ugly, but don't worry. I get -3 over root 13 squared is actually going to be 9 over 13 plus 2 over radical 13 squared. That's going to be 4 over 13. Well, that's going to be the square root of, what, 9 over 13 plus 14, 4 over 13 is 13 over 13, which is 1. Oh, that shows me the magnitude is 1. All right, so that's unit vector. Let's keep going here. Try not to take forever. Sorry, I got to erase all this stuff. There are a couple things that we do in vectors as well. We write them as a linear combination of I and j. So every once in a while you're going to see this. You're going to see 3i plus 2j. And you're going to be like, hey, mister, what the hell is that? Well, what this is it's 3 units. Here's I, so 3i, right? So 3 times this. So this is 3 times 1, 0, plus 2 times 0, comma 1, which is the vector 3, 0 plus 0, 2. Oh, well, that's simple. That's just the vector 3, 2. Why didn't you just say that? I don't know. Sometimes we just like to do extra stuff. Off the top of my head, I'm not 100% sure, but I'm sure it comes in handy with certain people. So if I said, hey, here's the vector 1, negative 7, you could rewrite this as 1i, if you want to put the 1, minus 7j. Those two vectors are exactly the same. It is as easy as that, so you can use both versions here, whatever works better. Okay, so here's another one of those interesting things. Why did we do something a couple minutes ago that we're just going to change? When we first look at vectors, we kind of look at slope, but really that's not how we do a lot of things. We actually look at a precise way of showing direction of a vector is actually using angles. So I told you don't forget your trigonometry because I don't want you to ever forget your trigonometry, and we're going to need it. So we need to figure out a direction angle, and since we can use points, we can use trigonometry. So if I said I had the point 3, comma 2 out here, this vector, I want to find this theta. So if I was to expand this a little bit, make this a little bit bigger, I went out 3 and up 2, and that means I can draw a triangle with side lengths of 3 and 2. Here's theta. Oh, well, that's nice. That's like our beginning trig. I know that tangent of theta is equal to 2/3, and therefore theta is tan inverse of 2/3. And if I do that on my calculator really quick, degrees are fine here. So let's go ahead and do degrees. I'm going to change mine. So tan inverse of 3 divided by 2, or sorry, 2 divided by 3, is, so theta in this case is 33.69 degrees. Likewise, on this version, it's the same thing. It's the tan theta equals y over x, so negative 5 over negative 2. So theta is equal to tan inverse of 5/2. So theta is equal to 68.19. Oops, sorry, 20, I guess, technically, for rounding. However, you better be paying attention because 68.2 degrees is in quadrant 1. However, this vector is in quadrant 3. So you got to remember your inverse rules. Here's 68 degrees. Here's the actual angle in question all the way around here. So you have to add 180 to get your actual answer, which is 248.20 degrees. So pay attention to the quadrants again, just like we did last chapter. Some of you guys are going to have nightmares because you didn't like it when we had it before. Lastly on this page, every vector can be written in trig form by doing this. It's the magnitude of the vector times, if you remember, cosine is the x, so it's cosine of theta, comma, sine of theta. Or you could write it as where the magnitude's on the inside, so magnitude v cosine theta, magnitude v sine theta. All right? So obviously you're going to need to find theta, that sort of idea. You could do that for this problem up here. You could do this for this one down there. Trig form of many different things come in handy, actually. Let's look at least at the first real world example here. Velocity is a vector, so we can represent speed as being the magnitude of the vector. And so if a jet is flying at a bearing, so again, that bearing word comes into play, at a bearing of 65 degrees at 500 miles per hour, what's the component form of the velocity of the plane? So this always gets people, so pay close attention right here. I know this video is getting a little bit long now, but really pay attention. Remember, bearing goes this direction. Here's 65 degrees. The speed is 500, which is actually the magnitude. So if we call this vector v, the magnitude is 500, and theta is not 65. It is not 65. It is not 65. I think I said that enough now. You have to do things in normal trig, not bearing. You have to look at this angle. The bearing is 65, but the angle is actually 25. So theta is 25 degrees. So the component form of this vector would be 500 cosine 25, 500 sine 25, and that would be that. And you can do lots of things with these real worlds. So you're going to see that in the textbook. I'm going to give a lot of time on this. I want to make sure we get these. These are really good real world problems. Okay, I'm going to finish us there. I'm going to leave you guys with this, and I will see you guys tomorrow.